So let's actually go ahead and start working and trying to get this figured out. We need to write down conditional density functions for each one of these pieces. Let's go ahead and start working on that. Now we've already done a lot of this work. We've already derived the mean and variance for U0, assuming that S0 was sent, and assuming that we had a specific value for phi. We've already done that math. If you recall, we already computed the mean. The mean was this, alpha sub 0 times cosine of phi. So if I knew what phi was, I could plug in here and get the mean. We already computed the variance. We call it sigma sum naught squared, and we had an expression for that. If you go back to the charts, we know exactly what this is equal to in terms of n naught over 2 and the norm of w sub 0 squared. So we already have done this basically. We can actually just take our mean and our variance. We know that it's Gaussian, and we can plug it into our Gaussian PDF equation. So this is the conditional density function given S0 was sent for a specific value for phi. It looks just like this. So we've already done that part really. The exact same thing for V0. We already did all this work. We've already derived the mean and variance for V0 under the assumption that S0 was sent for a specific value of phi. Our mean was minus alpha sine phi. We have the same variance. So we can plug into our Gaussian PDF to write down the conditional density function of V0 given signal 0 was sent for some specific value of phi. So that part is already done as well, so that's not too bad. So far we have 2 Gaussian PDFs. That's just 2 of the 4 though. We really need the other as well now. Remember, when S0 was sent for some specific value of the carrier phase, we derived that the branches trying to decode S1 turned out to just be noise components, and those noise components were X1 and Y1. So when you actually send me S0, the branches trying to dig out S1 just dug out noise. That's what we saw before. Both of these random variables, X1 and Y1, are Gaussian. They're zero mean, and their variance was sigma 1 squared. So remember, there was a dependence on I. For S0 being sent, the variance before on the previous charts, we had sigma 0 squared, which was n naught over 2 times the norm of w0 squared. Now we have the variance being sigma 1 squared, which is just n naught over 2 times the norm of w1 squared. So if you go back to previous charts, we had an expression written down exactly for what this was. So one thing that's interesting is there is no dependence on phi for x1 and y1. We did have a dependence on phi for u0 and v0, but we don't have it here. So what that means is when I go write down these density functions, after I write them down, if I look at it, there is no phi dependence. On the previous chart, we had a mean that had a cosine of phi. There was a phi dependence. So since there's no phi dependence right here, even though the equation I'm plugging into has a given phi, really there is no given phi. There's no phi dependence. So this is what we're looking for. The conditional density function for U1 given signal 0 sent for some specific value for phi. It's equal to this Gaussian PDF, and it just so happens that there actually is no phi dependence here. We can actually do the exact same thing here for Y1, or I'm sorry, for V1. V1 is just the distribution of Y1. It's just the noise part. It's a Gaussian PDF with a mean of 0 and a variance of sigma 1 squared. And again, there's no dependence on phi here. And that'll be important here on the following chart when we put all this stuff back together. So we've gotten a conditional PDF written out for each of the 4 components that we needed. Alright, so let's piece all of this together. If you remember what we're trying to do, we're trying to compute the conditional density function for z given signal S0 was sent. And what we said that we needed to do is we needed to integrate 1 over 2 pi from 0 to 2 pi of the conditional density function given 0 was sent over all possible values for phi. So if we go back a few charts, we had this integral equation that we needed to plug into, and we had a density function right here that we said was actually the product of 4 different individual density functions. So that's what we have here right now. We have 1, 2, 3, 4 individual density functions. I was able to bring these out of the integral. And the reason I can bring those out of the integral is on the previous chart we said they don't have any phi dependence. So this is an integral with respect to phi. These do not depend on phi, so they're constant with respect to that integral, so I was able to pull those out. The other two dimensions, though, do depend on phi. The conditional density function for u0, given signal 0 was sent for a specific value of phi, obviously depends on phi. Similarly, the conditional density function for v0, given signal 0 was sent, obviously depends on phi. So these I still have to multiply and average over all possible values for phi. So at this point, what we're down to working with is trying to work on this integral. So let's just focus on the integrand. Let's just focus on this part. This is just a Gaussian PDF, and this is just a Gaussian PDF. We wrote those down earlier. If I multiply them together, here's actually what I get out. Okay. If I simplify them a little bit, instead of having e to something times e to something, I can actually write it as e to both of those things added together. So instead of two e's, I just use one e, just using the property of exponentiation, adding those two arguments together. And let's do the analysis right here. Let's simplify this just a little bit. If I actually multiply all that out, so I've written the argument of the exponent right here. If I actually multiply all of that out, here is what I get. I get three different terms for the first squared being expanded, and I get three different terms for the second term being expanded. But if you recall, I have some nice expressions for the mean that I can use. We already have a nice expression for the mean of u0 and the mean of v0, and those expressions involved alpha naughts and cosines, things like that. So let's actually go to the next and let's plug those in. So recall, our mean of u0 was alpha 0 cosine phi, and our mean of v0 was minus alpha 0 sine of phi. So let's plug that into these pieces. That means that mu of u0 squared plus mu sub v0 squared turns into this. I square both of these things and I add them together, and you can see what happens. I can factor out an alpha naught squared, and then I end up with a cosine phi squared plus sine of phi squared, which is obviously equal to 1. So that gives me just alpha naught squared. So the integrand, after I expand the argument of the exponent and use this fact, actually simplifies quite a bit. It simplifies to this. Okay. So let's actually take this integrand and split it back up just a little bit more. We can actually split that back up into different pieces. You can see I factored this into two pieces, that piece and that piece, by just taking the square root. And then I have split the exponent up into three different exponents. I factored out one part right here, so that part I put here, this part I put here, and then the remaining pieces, this piece and this piece, I put over there. And having done this, we now have these extra terms right here. These no longer depend on phi, so I'll be able to factor those out of my integral as well. And really my integral now involves just trying to work with this. So this right here looks just like a zero mean Gaussian quantity, and this looks just like a zero mean Gaussian quantity. So we're going to call this random variable x0 and this random variable y0, because that's really what they are. They're just a zero mean with variance sigma 0 squared, so they're basically just noise. So we can use this fact on the next page, and we'll pull these out of the integral. So let's go ahead and do that. So here I've gone ahead and done that. These were the two new terms we just kind of factored out. They've been pulled outside of this integral. So has this, because this also does not depend on phi. And what I'm left with now is just this part right here. So we're getting there. We were trying to get a nice expression for the conditional density of our decision statistic z, and we knew we had this big integral to work through, and we've been able to simplify it so far into this times this integral, and we've been slowly working on this integral. So we've made a lot of progress, but there's still quite a bit left to do. We still need to finish working this integral, and we will continue doing that math and wrap up the optimum decision rule derivation in the next video.